Okay, so I'm going to talk for a few minutes about how our choices in terms of acquisition and processing can create artifacts in our seismic interpretation. So let's get going. So this is important to understand for a variety of reasons. We want to be able to identify these differences in our seismic data or in our seismic amplitudes or even machine learning outputs. And so I'm just going to go through some examples that show you some comparisons between different acquisition geometries like wide azimuth versus narrow azimuth surveys, show you the impact those have on imaging quality, and then I'll show you some examples from different survey design choices. So some dense versus conventional acquisition, long versus short offset. And all of these are things like, particularly if you get to plan a seismic survey, you want to take into account when you're doing your cost kind of benefit considerations. But I like to mention these because I think they're really important to understand in terms of quality control. So you as the seismic interpreter kind of have to understand what's going on. If you're working with most seismic data, you may want to have an input into changing the velocity model if you have kind of high velocity variations in the kind of geologic setting that you're working in, because all of these different things can help manage artifacts that you don't want to inaccurately identify as something with geologic meaning. Okay, so let's get started. I'm going to show you some acquisition and processing kind of quality control purposes. So you can use seismic attributes when you're doing quality control of your, you can't really go out and redo the acquisition, but if you're working on processing, your seismic attributes may help you see things in the seismic data. And so this is one example of that, where we've got our seismic data, the brute stack, the residual statics, and then the final migration. And you can look at it in your seismic time slice, but then you can also look at it in your coherence time slice. And so you can probably fairly quickly go through these and see the differences from the brute stack after the residual statics are removed, and then the final migration. And you could potentially identify areas where it's doing a good job, the processing has done a good job, or maybe there are areas that you may want to point out to try to clean up the data with a little bit more processing steps. So I highly recommend using your coherence in kind of evaluating your seismic processing. Here's another example of it showing the coherence after the initial velocity model and then from the original velocity model. Wait, I did that wrong. So your initial velocity models on the left and then your final velocity models on the right. And so you can see here by using and going back and redoing the velocity model, you get a huge improvement in terms of lateral resolution, particularly of these kind of thinner channels or less wide channels. Okay, so back in the day a little bit more, we often shot our seismic with more of a narrow azimuth as compared to a wider azimuth that we may use today. And so just to kind of remind you how these work, with narrow azimuths, you kind of roll through. So in this case, you're kind of laying out the line, recording, and then moving through. And so it ends up being a fairly narrow azimuth that you're able to collect. But nowadays, because the recording costs and the cost of the equipment has gone down, we've moved to doing more wide azimuth seismic acquisitions. In this case, you will have all of your kind of lines laid out. You'd have your shot point interval. And so you could see you're getting a much wider, larger azimuth in terms of the data that you're collecting. Okay. And so what I want to show you next is how this actually looks when you are comparing the seismic data from these two different surveys. And so this is an example of a dip magnitude map that was formed using the inline and the crossline components of dip. And so in this yellow rectangle right here, we have data from a 1995 survey that was narrow azimuth. Okay, and so you can see the noise in the dip. This red rectangle was shot later on, a few years later, with longer offset, but still narrow azimuth. So both narrow azimuth, red is narrow azimuth with longer offset. And again, it's still pretty noisy. It's a little bit better having the longer offset while still narrow azimuth if you're comparing the yellow to the red box. And then the larger survey outside of this was shot a few years later using wide azimuth and long offset. And so you can see all of these were kind of gone through again and reprocessed similarly so that you could do this comparison. But you'll notice that there's quite a lot of improvement and ease or confidence in interpretation when you're looking at the wide azimuth long offset survey that we're seeing here. So a lot less noise, more confidence in your interpretation. Here's another example that I'm going to show you of narrow versus wide azimuth acquisition. So I'll go back and forth. Here we've got our narrow azimuth and then our wide azimuth. And so as I go back and forth, you could probably notice that we've got better illumination in the wide azimuth acquisition. We've kind of got a lot less noise in it. So here's the narrow and then the wide, the narrow and the wide. So with the wide azimuth, you're able to kind of do a better removal of correlated noise features such as ground roll and multiples. And then also you get higher fold in the wide azimuth survey. And that can help with your velocity analysis also. So narrow and then wide. Okay, let's see if this video works. Hold on, I think I know what's going on with all my videos. I have to get out of the way. So this is an also in Seismic data. And so that's something we want to be aware of. Other things that we want to be aware of are examples of source generated noise. So I'm going to show you some examples of that next. So when, we kind of have our idealized, the energy goes down, bounces off a reflection and comes back up, but you can end up with multiples, you can end up with ground roll, you can end up with different types of scattering, diffractions. So all of that ends up in your seismic data. And so this is an example of a diffractor or kind of like an exploding reflector based on synthetic data that gives rise to a whole bunch of diffractions. And so you could see all those diffractions right below your target. And you can see them throughout the data. And so this is something we don't want to have to deal with. And the problem that we have with shallow diffractions is that you end up, let me try to think of a way to say this, is that they end up creating a lot of problems in your seismic data. So some of the ways that they kind of change the seismic image that can affect your interpretation is that they tend to have slower velocities. And so that changes where reflectors end up being put, and that ends up getting compounded when you do your normal move out in your processing. The diffractors tend to have broader bandwidths because they have that shorter travel path. So they're not being attenuated or absorbed in the earth quite as long. So that they'll also have higher frequencies than the real signal that you're interested in at depth. So higher frequencies, higher amplitudes, so they'll show up much brighter. And so there's a lot of ways that having diffractions in your data in terms of interpretation can really influence it. And so looking at all the noise that's generated when you have a lot of diffractions, like this is a nice kind of example where we have our horizons that we're interested in. We have a lot of, we've got our target horizon. We've got many, many, many diffractions. And so you can imagine if this was not just a simplified model that we were looking at, but rather something very complex with different lithologies, different geometries, a lot more different types of noise, that it would end up much more complex and introduce a lot of uncertainty in your seismic interpretation. Dense acquisition versus more widely spaced acquisition is also something that you want to pay attention to in terms of your seismic data. So this is an example in Oklahoma where we have a conventional a conventional seismic acquisition and a dense seismic acquisition. So you can see the difference in terms of spacing of the receivers and the source, which results in the bin size that we use during seismic processing. And so conventional, dense. And so let's look at it in seismic data, because I always feel like that's the important thing to do. And so we've got our conventional on the left-hand side, our dense on the right-hand side. And you'll notice that the dense survey gives you a much better image of some of the more steeply dipping features, and I'll kind of highlight them here. We've got a very subtle fault that I'm highlighting in this red oval, and then over on the other side you can see those much improved steeply dipping features. Here's another quick example comparing the conventional with the dense acquisition. So again, these red ovals are kind of highlighting areas where we've got significant improvement. In this case, it's simply just of imaging some of the steeper dips. You can actually see there's some small scale offsets up here in this region that are picked up by the dense acquisition, but not the conventional acquisition. Same in here, we've got kind of higher resolution. I'm able to pick out more horizons, which depending on what I'm interested in interpreting may be of interest. So we've kind of got some higher frequencies here. We also have some sort of offset or undulating pattern in these bright reflectors that may be of significance. Here's another example where I'm going to show wide versus narrow azimuths in karst reservoirs. And so these are with sand dunes, which is kind of cool too. So we've got sand dunes and we've got karst reservoirs. And so here we've got our narrow azimuth data and then our wide azimuth data. And so to me, like just looking at this really quickly with the wide azimuth data, I'd be very much more confident in picking out all of these fractured kind of cave reservoirs in here. You can see they're higher amplitude. The data is less noisy because of the higher fold. And so if these were a feature that I was interested in interpreting, I would much rather work with the wide azimuth data. Looking at a kind of arbitrary line that connects these different karst zones for the wide azimuth versus the full azimuth, you can see that we've kind of got a much better identification of the smaller scale reservoirs down here where we're looking at the full azimuth. So now you can see kind of how we filled in. I didn't point that out on the last slide. So here's narrow, wide. So we've got full to 72. Here we've got the full azimuth. So it's been further kind of reprocessed to get azimuth in 360 degrees. And so that helps even better than wide azimuth in identifying the small scale features. Okay, and here is a example of showing coherence that's been computed on the narrow, the wide, and then the full azimuth survey. So we're starting here with the narrow azimuth. Here is the wide azimuth, so we're seeing a lot more information, a lot more continuity in this coherence image. And then here's the full azimuth survey. So much clearer, much more confident in our interpretations using full azimuth data than the wide, even though wide is much better than the narrow. So things to keep in mind. In this case, what was done for this study is they merged two narrow azimuth surveys to simulate that wide azimuth survey. And so that's how some of this information was collected. And so here you can see how they've got just one narrow azimuth, so survey B only, versus the merged surveys that help simulate. So if you don't have the ability to go out and shoot a whole new wide or full azimuth survey, you can merge ones that are both narrow azimuth to get better azimuthal coverage. And so this is just an example. You can see a lot less noise, a lot more confidence in the scale and size of these karstic systems. And then here's looking at the narrow azimuth survey. The two narrow azimuth surveys combined, so kind of simulating that wide azimuth survey. And then just to talk for a few minutes about longer offsets. So short versus long offsets, this is kind of like the offsets that you have if you're trailing geophones through hydrophones through the ocean. You may have a 5-kilometer cable, you may have a 10-kilometer cable, but long offsets are typically preferred because they can kind of provide a little bit more leverage against having too many multiples, but they can be very sensitive to anisotropy, so you want to keep that in mind. So they have kind of their pros and cons. It's a little bit more to process. But let me just show you an example of this. So here we've got our short azimuth and then our long azimuth. And so you can see with kind of the short azimuth and applying a mute and then looking at this area of interest here from this 2004 paper, the difference in terms of the seismic horizon, the continuity of it, the structure of it. You think about your confidence as a seismic interpreter. And then one more for dense acquisition. Here we've got a single vibrator versus more widely separated vibrator arrays. And so this is a study done in Egypt. So the slip sweep acquisition and then the more detailed vibrator arrays over here on the right hand side. And so you could clearly see the difference in acquisition footprint. So you've got that vertical striping, and so that's something you kind of want to be aware of in interpreting. I don't know, I've been interpreting so long, I just kind of mentally filter out acquisition footprint, but it's not the easiest to do. Here's another example where we've got kind of lower density surveys on the left-hand side and then a higher density survey on the right-hand side. And in these areas of interest or, areas of focus, you can really see the difference in terms of the structure. Whereas here with this lower kind of dotted oval, you can see that it just looks very, very noisy. Whereas in this higher trace density survey, you can actually see some structure in that area. And then same thing up here in the higher one. Other thing to notice is that in the lower density survey, you're missing a lot of the shallow data than your offset data. So just things to keep in mind as you're, working with the data that you most likely have been given. Other things to think about are frequencies. So you can work with different types of frequencies, depending on how your survey was collected. Vibra size can have different frequencies, and in that example I just showed, you could see that the older survey was missing some of these lower frequencies, so they were missing on that legacy survey. And if we go back and look at it, we can see the newly collected data along what looks like perhaps a fault or something that I wouldn't have been able to identify in the legacy data, even though they tried to enhance it and re-migrate everything. There's a lot of variation, there's a lot of structure missing in this kind of yellow highlighted area between the legacy data and then the newly collected data that has that wider frequency zone. And then here's a few more examples. So again, now we're looking at the legacy on the left-hand side, and then the more recently collected data on the right-hand side, higher density data with the incoherence, so kind of like a variance type attribute with a different type of seismic attribute. And so you'll notice huge variations in terms of incoherence. You can look at this and think about, again, how you as an interpreter would have confidence in your interpretation in terms of the data. Here we've got positive curvature on the left-hand side from the legacy data, positive curvature on the right-hand side. So we can see that the newer data, the higher density data, is picking up a lot more flexures in the subsurface. We've got dip azimuth, dip angle. Again, we're seeing more detail because of the higher density, because of the more full frequency range of the newer data. But we're still getting the general trends from the legacy data, so you don't need to throw it out. So in any case, hopefully this just kind of gave you an idea of when you're working with your data and you're looking at your data, particularly if you're working with more legacy or older data that was collected, last century, of things you just want to be aware of when you're interpreting and using seismic attributes. So we don't always have the ability to go out and collect new data, have the highest quality data. I know my students often complain if I ask them to do a project on 2D data because they want to do everything on 3D data, but there's still so much information in 2D data. So the wider azimuth that you have, the better. You can take narrow azimuth data and synthetically kind of combine it to make a pseudo wide azimuth survey like I showed you. Longer offsets are typically better, but there are some things you want to be worried about with them. And yeah, I think, one of the things, just going back through this when I was making the summary slide, is some of the big differences that really showed up in terms of interpretation with just the examples I was showing is the better quality data, the better you're able to image those steeply dipping structures, as well as seeing faults that don't have a large offset. And overall, it's all about giving us more confidence in our seismic interpretation. So as always, thank you for listening.